again. Okay, reaction curves and equilibrium. We're going to talk about a couple of reaction curves today. One of them is having to do with effective and ineffective collisions. So if you have an effective collision, that's like you see a cute guy and you approach it correctly. If you have an ineffective collision, you go and go, oh, Drew, you're so cute. You know, you might not have the same effect. Yeah, you might not. Okay, same thing with a guy. So you need to have the right amount of energy and the right orientation, okay, to get an effective collision. That's a shortcut from what we were doing. This right here is known as an activation curve. You will need to be able to draw an activation curve. So we're going to talk about different parts. You've got the reactants, you've got the products. This is an activation curve for an exothermic reaction, meaning it will give off energy. It gives off this much energy. So this is known as delta E, and that didn't show very well, but that's a delta E. The energy from here to here is known as activation energy. This is known as E of A, and that didn't write very well either. But it's capital E, lowercase a, and it's a subscript. From here to the top of the curve is what's known as E of A prime, and it really wants to do funky things there. E of A prime tells me if I went backwards, if I started at my products and I went to my reactants, Grayson, then I would need that much energy to get up over the curve. Okay? So talking about the boy and girl scenario. Here I am, and we're separate. I need to put enough energy into meeting that person before anything can happen. Okay? So any reaction has to have a bit of energy to get started. If I give energy off and I end up lower, I'm exothermic. If I end up higher, say I ended here as my products here, it would be an endothermic reaction. Okay? Now we're going to do a couple of these and see if we can write them down and try them. So I'll go through the first one with you before. This just shows right here, if I try to find the one, okay? I want to find the one that I live in love with and he's in love with me and we're going to get married, okay? I can either do like we do now and go on lots and lots of dates trying to find the one, or I can do like they do in the old world and ask a matchmaker and say, this is the list of things I want in a guy. Go find him. With the matchmaker, I use less energy and less money than if I go on dates and 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 try and find the one. Now, it might not be exactly what I want unless I put everything I want on that list, and the matchmaker finds everything on that list. Okay? But a matchmaker, or what we call a catalyst, I just love how it's taking and making those all arrows. That's wonderful. A catalyst actually lowers the activation energy. Okay? So activation energy is lowered. So it shows it here for on this side for an endothermic reaction, on this side over here for an exothermic reaction. So delta H is negative for exo, delta H is positive for endo. Okay, so we're going to try and draw one. So I want you to try it with me, and we're going to draw one together, and then right after this we're going to draw one by yourself and see if you can get it right. Okay? The first thing is you want to always start at 0. You want your reactants to start at 0, no matter where you are. So we're going to put our reactants right on the 0 line. So make yourself a graph and make that 0 right there. Okay? You're going to want to be able to go up and down from that 0 point. Okay? It says here that the delta E forward is a negative 60. Negative 60. That means it's down below 60 where I started. So there's my delta E. I'm down 60. That means my products are going to end up over here. What does every reaction have to have? What did I just tell you? Every reaction had to have an activation energy. I have to get up off my butt to go meet that guy, right? I can't just sit there and hope he comes. Okay? So right here, we've got activation energy. It's going to take 80 kilojoules to get this reaction started. So I've got to come up to 80. Come on. I've got to go up to 80 and then back down to the products. So I can label my delta E. I can label my E of A. Now, what would be my E of A prime? Going from the products to the top of the curve. So if I go from the products to the top of the curve, I get my E of A prime. Yes?
So how come the delta, is that what it's called?
Mm-hmm.
The delta E backward?
Uh-huh.
How come that, because that's labeled right now EA, how come that's not?
So this right here is a distance between the reactant and the product. Yeah, if I'm going from my reactant to my product, I've given off energy, so it's negative. Going from my product to my reactant, I had to add energy.
Yeah, you have to add 60, so I'm just wondering why it's labeled EA versus delta E. Right?
EA right here represents this.
Oh, so then where's the plus 60?
Right here, delta E is just which way I'm going.
Oh,
The only thing that's going to change here is just the signs. Activation energy was given. Okay, activation energy or the E of A prime will be given, because otherwise you won't be able to draw the graph. It's from products to the top of the curve, which is, okay, good question. So we know E of A is 60. Sorry, we know delta E is 60. We know E of A is 80. So 60 plus 80 is 140. So you need to be able to draw one of these graphs. So we're going to take a practice now where I just give you information. I'm going to give you some time, and you're going to try and draw the graph. Okay? So, yep, I can hold on 1 second. Does that make sense for these? Sorry, whoops.
So even if they didn't list that there was like a forward and a backward, you'd always know that there's the backward would be positive, the same number?
Well, it would be whatever the sign is reversed.
Okay.
Yes. 140 is the 60 here and the 80 here. So the total distance from the product to the top of the curve. Okay, going forward, let's see what you can do on your own. This is what I give you. See if you can draw the curve and see if you do it right. We're going to put it up here in just a second. What do you guys think? Is it going to be an endothermic reaction? If I have to add energy into it? Yeah. If I have to add energy into it, this curve is going to be an endothermic, not an exothermic like the one before. So the products are going to be 40 above where the reactants start. Okay, if you're stuck, I'm just going to, every few seconds, I'm going to push the button so you get a little bit more. If you're not stuck and you got the initial information, keep writing down what you think it is, and we'll go from there. If you're stuck, write down as it comes up, write it down so you can follow hopefully later. How do we do? Were you able to figure it out? Any questions on how we got something? Yes. E of A prime is just from where the products are to the top of the activation curve. Okay? Yes.
The E backwards, is that just always a negative?
It's not always a negative, no. Delta E backwards, it's opposite the sign of whatever forward is. That's the only difference.
So
Okay.
the product's always going to be where the delta E reaches.
Yeah, you're going to go from the reactants to wherever the products are for delta E.
Will you always be able to do an activation curve if you're even given one of those pieces of information?
You need two. You need delta E either forward or reverse, and you need E of A or E of A prime. Okay? So this is one of the curves that you're going to need to draw in your worksheet tonight. Okay? So one possible. We're going to stop on this, and we're going to go to an activity. I want to stop. It's not letting me stop. Okay, we're going to go to an activity. What I'd like to do is you have the computers up, yes? Okay, and you should be up on the blog. Okay, so you should be up on the blog. Let me see if mine went down, so I've got to bring it up. So go to faculty and staff, go to my website, go from my website. You can actually go, instead of going to the blog, you can go right to the online textbook. And on the online textbook, okay, you should come up with this screen. On this screen, I want you to go to your to-do list and scroll down until you see heat curve or make a heat curve. I actually put it in there twice because I wanted to make sure you got it. Okay? And you can follow the instructions of either one. I don't care what, but everybody in your group needs to make a curve, a heat curve. And we're going to label it later, so you want to make it big enough that you can see what's going on. So you can do every 30 seconds or you can do every 15 seconds. So when you get this up, you want to press this little flower right here, and it'll bring it up. Username and password should just be your username and password. Yes. It was either a D or an N. It has a solid. Okay, it has a solid right now. So as you're doing the experiment, make sure you choose water, and as you push go, get right over the pause so that you can stop it every 30 seconds and write down what the temperature is. You're going to make a graph. Okay? Everybody okay? So you can do a data table and do the graph after, or you can do the graph as you go. I don't care which one.
Is it like a heat curve graph?
So I want, yeah.
So it's what we were just doing.
No. No. That was an activation curve graph.
So what's it?
Heat curve graph is what you're going to find out is. So if you've got your composition notebooks and you're going to put it in that, turn it sideways. Okay? Either way, you're going to need to turn it in. Okay, so you might not want to do it in your composition notebooks. You might want to just do it on a plain piece of paper and turn it in. I think I have some graph paper, so let me go check real quick and I'll see if I do. So you should have had time to do your heat curve from your thing. If you haven't, you need to graph that. You need to make sure you label it heat curve and make your name on it because you're going to turn it in for credit. But you're also going to be using it later for more information. So make sure that you do write everything that I have on there. It is a heat curve. So far this time we've learned phase diagram, activation energy, and heat curve. And you need to know the difference between all of them. So going with the heat curve, this is basically what you should have got. Okay? going up to about 115. Basically what you should have got. What we're going to do is we're going to label this. Every time there is a positive slope, every time there is a positive slope, that means here, here, write this on your heat curve, and here, you're going to use this equation. And this equation is Q equals mCp delta T. We're going to explain that. Q is heat energy. Okay, Q is heat energy. M is mass. It's pretty easy. Cp is specific heat. Now this one, Cp, changes at each of these levels. So here, Cp is different than here. It's a new Cp. So I'll put Cp1, Cp2. And up here, Cp would be even different, a different Cp. So every place, it's a different thing. Basically, specific heat is how much energy does it take to raise 1 gram of that substance 1 degree Celsius. Okay? So this is the equation we're going to use. Delta T is just change in temperature. Okay, let's label what state we have at each of these. This area right here, we had a solid. This area right here, we had a liquid. And this area right here, we had a gas. So what was happening on those flat areas? What was going on in the flat areas? What about this first flat area here at 0? Quentin?
It's like gaining energy.
It's gaining energy, but it wasn't getting any hotter. So what was changing? Did you look at the picture when you were doing that?
The mass.
What was changing? I was changing state. I was going from a solid to a liquid. Okay, so here I was melting if I'm going that way, or I would be freezing if I'm going this way, right? So what we use here is heat of fusion. And we take heat of fusion times mass or moles, depending on what heat of fusion is given in, to get the change in heat of fusion. And that little F means fusion. Fusion has to be doing with freezing. So what was happening up here on this long 100 stretch that you guys were all dying? Is it going to change? What's happening? From a liquid to a gas, what's happening? Okay, evaporation. We also call that boiling, right? Depending on how vigorous it is. What about going this way? Condensation, good. That was a horrible arrow. Okay, here the equation is close to what this one was, and I guess I should have written that one in red, so I'm going to write this one in red. This one is the heat of vaporization is equal, well, delta H heat vaporization is equal to heat of vaporization of my substance times the mass, or again, it could be mole, depending on what heat of vaporization is given it. Okay, we also call, and I'm going to pick another color. Let's pick purple. We also call this area right here, from here to here, this is Q1, or the first amount of energy that we put in. From here to here, we call this Q2. From here to here, we call this Q3. Okay, so just different areas. So when I'm in the solid Q1, when I'm melting or freezing, Q2, Q3. This area right here, Q4. And this one on up is Q5. Okay, we're going to be using this to actually solve for how much energy it takes to melt an ice cube. How much energy it takes to evaporate some liquid. Okay? Q3 is from melting this flat part here up to where I'm boiling. Okay? I'm hoping yours looks a little better than mine because I had a little squished area. Okay? So we're going to use this next time. Yeah, I want you to draw that on the graph. Now I'm going to put this on the internet, on the blog, so you can get to it. The worksheet that I gave you, we're going to work on it next time because, okay, we're going to work on it next time because we didn't have a lot of time in class, so we're going to work on it next time. And we'll finish up this graph and work on some problems with this graph next time, so don't hand it in yet. Okay? Q5 is from boiling on up where you have gas. Okay? Please make sure you log all the way out of the computers because I've had groups come in and open up the computers and people have forgotten to log out, and then you have a problem because they can mess with your account. Okay, so make sure you're all the way off of it.
Okay.